A woodchuck would chuck as much as it could if a woodchuck could chuck wood. You don't get what? So I have obviously made a mistake down here at heptane. This should not be C2H6. Ha 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 ha. It should be C7H16. Okay. How are we doing? Are we almost done? Maybe. Structure drawing takes a long time. You're right, it does. Yes. No, because that's not required for AP. So I'm not going to stress about anything that's not required for AP. Okay. The reason I want to present it to you is because it's kind of nice to know, because when you go to university, you will probably be expected to know how to derive those things. Yes. A methyl group. Okay, so if you have a carbon chain, so let's say, what would this one be? If we had like this, what would its name be? Those are all hydrogens. Butane, okay. Now, if instead of having a hydrogen, so if all of these are hydrogens, but sticking off of one of them, instead we have a CH3, that's a methyl group. So it's like a branch.
Does it have to be,
Yeah, it'll be a C with 3 hydrogens is methyl. You could have an ethyl group that is 2 C's with the appropriate amount of hydrogens. Yeah, it's methane but stuck onto another structure. Kind of, you know, when they name them, what they do is they find the longest chain of carbon atoms. So they will say, okay, here's my longest chain, which is 4 carbon atoms long. And then they name anything that's sticking off the side. Okay? So this would be called methyl butane. Okay? Because there's really, and we don't even have to put a number on it because there's nowhere else you can put it on butane. Because if we were to move our methyl group to, say, here, okay, that is an equivalent structure because it's still on the second carbon from the end, right? I've got a second carbon from the end here, and I've got a second carbon from the end here. Those are comparable carbons, right? I cannot put a methyl group here because then now I have pentane instead of butane, right? Because now I just have a 5 carbon chain instead of a. I can put it on those. I can put it on any of the ones that I've circled in red. The methyl group could go anywhere, and those would all be equivalent structures. What about the other 8, like the ones on the ends? Watch what happens. These guys. These ones. Whoa. Because guess what? Our longest chain. Sorry. I would have butane, and then if I put it up here, that's still pentane. And it doesn't matter because, quite frankly, the structures are not actually linear like that. The carbons actually zigzag. They go like this. You just say how many C's are connected to each other in a row, right? And you could say, here's all my hydrogens. Okay, so that is no different. That's exactly the same structure as, yeah, those are both pentane. Yeah. And the reason it looks different for one and different for the other is just because we're just drawing everything at right angles, but nothing's actually at right angles. Everything's at 109.5. Yeah. So are we ready to do this next part together? What did you notice about the name of the ending? We take the alkane name and what do we do with it? Oic acid, oic. Okay, so we have now learned 2 different functional groups. Functional groups are specific molecular structures that stick on to organic compounds, okay? So specific molecular structures stuck onto a hydrocarbon, and that does not include things like a methyl group. That's just considered a branched hydrocarbon. Yes? Yes, exactly. So all the carboxylic acids behave as acids. Because every single carboxylic acid has this structure here. we call this entire structure where we have a carbon double bonded to a, yeah, exactly, double bonded to an oxygen with a single bond to another oxygen and then an H. That entire thing is called a carboxyl group. That is the functional group. Yes. Okay, so acetic acid is actually ethanoic acid. They're the same thing. Yes? Yeah, just different names. Acetic acid is a common name. Obviously, before they knew about organic chemistry, people have been making vinegar for ages, right? So they named it well before they named the organic compounds. Yes? Yeah. Well, if you were to put your carbon on, like, let's say we put it here, that would be then butanoic acid, right? But if you put it here, that would be methyl propanoic acid. Yes. Okay. The functional group is specifically this. Okay, when we say functional group, we mean the bit that makes it an acid. Okay, so this bit here is the bit that makes it an acid. The rest is the carbon chain, and the carbon chain can be a straight chain, yeah, or it can be a branched chain. All right, but we often refer to this bit, this hydrocarbon chain that is attached to the functional group. This is referred to as R. And I always say that just refers to the rest of the molecule. Okay, that's how I remember R. And the rest of the molecule will be a hydrocarbon chain. Yeah. An alcohol is not an acid. So an alcohol, if we had an alcohol, our functional group would just be the, whoops. Yeah, making mess. Sorry. The functional group is just the OH. Okay, so that is the functional group for an alcohol. There isn't one. It's just a hydrocarbon chain. Functional groups are things, extra bits that are different than carbon and hydrogen that you stick onto a hydrocarbon chain. So, for example, we have our hydrocarbon chain here where all of these little bits are hydrogen and carbon. And if we stick an OH on it, now we have an alcohol. If we have a hydrocarbon chain and we stick a C double bond OH, then we have a carboxylic acid. If we had a carbon chain and we stuck a nitrogen on it, this functional group is called an amine. Okay? No, you don't need to know that. I'm just giving examples of things that are functional groups. They just get stuck on, and you could stick it on the end, or you could stick it in the middle, okay? You can have more than one functional group on something, especially, watch this. So we have an amine group, and we have a carboxyl group. And carboxyl groups belong to the carboxylic acids. So we have an amine and we have an acid. Guess what we have? We have an amino acid. Now, I don't know if there's any that are that simple. I think there's other bits in there that are much more complicated, but that's the general idea of an amino acid, is that you have an amine group somewhere and you have a carboxyl group somewhere else. I can't remember what they're like. I've got a book here somewhere, but we could look that up some other time. How does that sound? Okay, so that's the idea of a functional group. And we're really only focusing on the ones that we can do reactions with in this unit. And so those would be our alcohols, which can burn, right, combustion. And then we have our carboxylic acid groups, which can, of course, function as acids. And so we will see those in neutralizations. Huh? Yes. There we go. How's that? So we don't always write out the COOH as C double bond O single bond OH. Sometimes we just write it as COOH, sticking off the end. You can also see it written as CO2H. I don't see it that often like that though, but different textbooks do different things, okay? And here we have the letter R, yes. That's the rest of the molecule over here, the rest of the molecule. And carboxylic acids are found in amino acids. They are found in proteins. They are found in fatty acids. And they are found in oils. And they are found in intermediates of carbohydrate metabolism. Do you need to know any of that? No, not for this course. You just be like, okay, that's nice. So why are they acidic? Okay, so when you have this hydrocarbon, you know, you'd have all these hydrogens over here, right? You're like, oh, so many hydrogens to choose between. Which one's going to fall off? Well, what do you know about the electronegativity of oxygen? Oxygen has a high electronegativity. So what that means is that if we were to draw our dipole moments, yes, and in fact, you know those dipole arrows we've been drawing? We often refer to them as dipole moments. I don't know why. It's not like a moment in time. A dipole moment, just think of it as a dipole, okay? So if you hear the word, don't get freaked out. Just be like, oh, okay. Thanks, Miss Spence, for giving us another word to know, all right? So when we draw our dipole arrow on the carbon and oxygen here, what would our dipole arrow look like? Would it be pointing up or down? Pointing up, okay? So there's our dipole arrow there. And when we have our dipole arrow between the oxygen and the hydrogen, that's also pointing to the left here. So we got one pointing to the left. Okay. And remember that hydrogen has only a single proton, yes? So in general, we have this overall motion of electrons this way. Yes? We're kind of going swoosh. Yes? Overall motion of electrons that way. And what will happen is that hydrogen will then, because of the electron density close to the hydrogen, you know, if we were to draw our actual bond there, you know, we would have like, oh, little electrons, most of the electrons, oh, a little bit over here, right? And given the opportunity, this hydrogen can just fall off, yes, and leave the electrons behind. It's a hydroxyl group. Because the dipole is not as strong here. And there's something special about hydrogen in the fact that it's just a single proton. It's not that attractive to those bonding electrons. It's like, bye, see you later. Yeah. Yeah, H is like happy to go off on its own. Okay? So the H can actually then come off and become H plus. Okay? So this is what it ends up looking like. This bond here is made of 2 electrons, yes? And those electrons get left behind, yes? So those were formerly bonding electrons, and now they are just a lone pair. What? Because the oxygen pulls the electrons away from it. Because oxygen says, electrons, they're all mine, and the hydrogen's like, okay, bye. The electrons are all gone, so I will now float away. Yeah, it very much acts like an ion, okay? And in fact, when it comes off, it becomes an ion. Yeah? So we actually would have, and I forgot to put it on here, which is terrible, this entire thing, this entire structure here would have a negative charge. Okay? Yes? Yes. Yes. It doesn't, acetate itself is fairly soluble, so it doesn't do it very often, but it could. I think if you put it with mercury, maybe. Not sure. Yes. You can have certain things happen with that. Like, for example, here's one that you all know about, DNA. DNA, one strand bonds to the other strand. Although those ones are not covalent bonds, those ones are hydrogen bonds, which are a form of intermolecular force. Okay? But yeah, you can have structures bond to themselves in ring structures, things like that. Yeah.
Oh, like the nitrogen.
Yes. Okay, so that should be a negative ion there. I just forgot to draw it on. Okay, so it should be a negative. I've labeled the negative because it looks like I've just drawn a line randomly. Okay. It's like floating in the middle of nowhere. The negative charge would actually be like down on this oxygen because it's got that extra electron in that lone pair. Okay. So when you draw the dissociation of these acids, it's always that terminal hydrogen that falls off. It's not the hydrogens on the carbons. Okay? Okay, So, if we had our carboxylic acid reacting with sodium hydroxide, just like any other double replacement reaction, or neutralization, our H and our OH would get together, of course, and form water. And we would end up with the sodium ion, which is positive, getting together with the carboxylate ion, which is negative. And even though this would be soluble, if you were to then evaporate the water, you would be left with sodium acetate salt. Yes? This would be aqueous. This would be aqueous. But if we evaporate the water, remember, all we've got left is we've got sodium and we have acetate. I'm just going to call it AC, okay, acetate. Now what happens if we evaporate the water? You get the solid salt forming, okay? The crystal lattice will form. Okay? So, writing the molecular formula. I don't know how important it is that you can do this, but if we have, say, hexanoic acid, you can say, okay, hexanoic means I got 1, 2, 3, 4, 5, 6 carbons, yes? And I know that that final carbon has a COOH on it, yes? So I can ignore that one. Oh, hang on, 1, 2, 3, 4, 5, 6. That's wrong, that should be C5H. And then it's going to be twice the number of carbons, right? Plus 1. So twice the number of carbons would be 11, and then we have our COOH on the end. Okay, is it really important for you to be able to figure that out? No. All right, I'm not going to make you figure those out. You'll have your table of things. Did I get that right? Yes. AP is only going to give you like really common ions, or it'll tell you what the structure is. Because they've moved away from a lot of memorization, which I quite like, because, you know, do you really need to memorize all your common ions? My God, we used to have to memorize and we used to have to memorize all the solubility rules, and there were little mnemonics that you had to remember for each of them. Oh my God. Okay. Anyway, you enjoy what? Me eat peanut butter. There are some good ones, but you know, it gets tiresome when that's all you do. So you can practice these, and then you can write the names, and then you can balance those, okay? Your homework, pages 92 to 95. So do this for right now, and then pages 92 to 95. So that would be like all of pages 90 to 95.
You're Muslim. Like, come on. He's talking about halal. No. Okay. It's like it looks like you're walking. It looks really nice. Really cool. It looks what is a whole It's a religious thing, yeah. Yeah. Muslim it's a religious very it's very heavy. You're not I mean I mean my friends that sounds so cool. Now we met a child. It's a giant ball. Okay, so if you're looking at a map, this is west, this is east, this is north, this is south. It spells we. It spells we and it spells sour. In between, okay, I'll find it again. It's in between Europe. Look at them. They're like Wait, so what are you, why are you, how are you trying to I can